to understand, but its ramifications for different systems, it's pretty, yeah, it has huge implications for various aspects of materials science. We'll take a look at the essence of nucleation, which is very easy to understand, and it is geometry. It has really nothing much to do with materials. So imagine you're forming a solid from a liquid. So if the liquid is cooled to a temperature below its melting temperature, the solid definitely is more stable. So in terms of thermodynamics, we say that the free energy of the solid per unit volume is lower than the free energy of the liquid. So one uses the symbol delta G sub V, liquid to solid. That is the driving force for solidification. Even though it is an energy, I mean, the term driving force sort of stuck in the literature. So if this delta G for a process is negative, then that process is possible. So we are below the melting temperature, and therefore formation of a little bit of solid is preferred. But the problem with the nucleation is the fact that there is an interface that you form. And as we have seen in our discussion of defects, any defect that you form has a positive energy. So that is the key problem here. So formation of a little bit of the solid from a vast ocean of liquid involves a negative contribution due to this change in the free energy, and a positive contribution due to the formation of a surface which originally did not exist in the liquid. So that is a key, and let's see how it plays out. So the geometry that I told you about is that the area, the energy due to the increase in the size of this small clump will go as the area, and the area goes as 4 pi r squared if you assume a spherical particle. You can assume any shape, it doesn't matter. It will give you basically the same result. And of course, the volume goes as pi r cubed. So that is effectively what we have here. So the negative contribution goes as r cubed, and the positive contribution goes as r squared. And so the bottom line is that the second term, which is that term here, it always wins at small enough values of r. I mean, for example, if you just plot r squared and r cubed as a function of x, for x values below 1, you know that r squared is bigger than r cubed. So that is basically the stuff here. So in this case, this is the second term is positive, whereas the first term is negative. And at small enough values of r, the positive term always wins. And therefore, if you think in terms of the free energy change, overall free energy change due to the formation of this small cluster, small clump of solid, the free energy has to go up first before it starts to decline. So one worries about this size, critical size at which this free energy reaches its maximum, and the maximum value of the free energy is given designated using the symbol delta G star, and of course the size itself is designated using r star. So since you can compute delta G star quite readily. Oops, I mean some error here. Anyway, we can find first r star by setting the first derivative of delta G with respect to r at the value of r star to 0. And so this is the expression that you get. This, of course, is geometry dependent. We have assumed a spherical shape for the clump of solid. And substituting this value back in the expression for delta G, you get this expression for delta G star. It goes as the cube of gamma, and also it goes inversely as the square of the driving force. And in the R star expression, there is a negative sign because the denominator is by definition negative. If it is not negative, then the whole thing doesn't work anyway. So yeah, since delta GV is negative, you need a negative sign here to account for it, to get R star to be some positive finite value. Okay, we can go through the rest of the arguments. The main thing, of course, is that nucleation is difficult. Why is it difficult? So it is difficult because anything that increases the free energy depends entirely on chance fluctuations. Then we are now talking in terms of probabilities. So to create a viable solid nucleus, which can actually grow beyond once it reaches R star, from that point onwards, further growth basically decreases the free energy. Therefore, there is no problem at all. So, but reaching this viable status for the nucleus is difficult because you need fluctuations that achieve this value of delta G star. So these fluctuations are less probable for nuclei with higher values of delta G star. So one is always looking, I mean, from a theoretical viewpoint, one is always looking for ways of decreasing this value of delta G star. And this also implies, going back to this delta G star expression, delta G star is effectively infinite when there is no driving force. When the driving force is zero, which means right at the melting temperature, it is difficult to, it is infinitely difficult to nucleate a solid at the melting temperature. So that's because this delta G star at that temperature is infinity. But of course, as you decrease the temperature, okay, one uses this jargon here called undercooling. Okay, in Veritas video, he kept calling it supercooling, which is a pretty common term. But technically, this is what this is a term that one uses, undercooling, and so which is defined as Tm minus T. As this undercooling increases or as temperature drops, the driving force definitely increases. That means delta GV, delta G sub V, that is the driving force per unit volume, becomes more negative. And therefore, this is delta G star. Delta G star keeps dropping. And therefore, we make nucleation more and more probable at larger and larger undercoolings. At small undercoolings, of course, it is possible to keep the liquid stabilized for a very long time indeed. And so that is a video that you just saw. And so you can actually play all kinds of neat tricks with super cold water. Just check YouTube for this phrase, super cold water, and you'll find a whole bunch of things there. Okay, the next point that we want to look at is the methods to aid nucleation. Nucleation is definitely difficult, but it is not impossible when there is a finite driving force, which is why, I mean, even in a freezer, in the case of the video, the guy had to take the bottle out after some finite time. If he leaves it there for a little too long, solidification would have set in and it would have ruined this experiment. At the beginning of the video, he also talks about why, about the unexpected difficulties that he faced in recording that video. He tried many, many things, and in some cases, I'm pretty sure the solidification would already have begun. And therefore, he could not show it as an interesting video. So when there is a finite driving force, such as keeping water inside the freezer, nucleation is difficult, but it is not impossible. So it will have to eventually happen, but you can decrease this time for nucleation to happen by resorting to various techniques. So, but before doing that, I mean, we need to say this. It's a very general phenomenon for all kinds of transformations. In the case of crystal growth, from either the gas phase or from the liquid phase. You are trying to grow a solid under controlled circumstances. You have to worry about nucleation, and you have to create conditions that make nucleation easier. And and of course, gas to liquid transformation, such as rain formation in clouds. Again, it is an issue. In many cases, I mean, we keep reading in the newspaper about the government resorting to experiments with cloud seeding. And that is basically to somehow coax the cloud into forming rain. It already has water stored in it, but water in the form of liquid water droplets in the form of rain is unable to form in such clouds because of difficulties with nucleation. So by using cloud seeding techniques, you can actually make this process happen. And of course, nucleation is definitely, I mean, from the equation, we can see that nucleation is easier at the higher driving forces. And nucleation is also easier if the interfacial energy is lower. This is for all transformations. I mean, it is difficult to see for liquid to solid transformation how the interfacial energy can be lower. But in the case of solid to solid transformations, we will, I mean, eventually you will study various kinds of solid to solid interfaces. And in those cases, there are specific ways, specific interfaces between solids which have a low energy. And so you can try to create such, at least nature does choose these things rather in a straightforward fashion. But we will have to do some research to understand why those interfaces have a lower energy and so on. But it is at least considering several different possibilities for the solid, you can say that that solid with the lowest possible interfacial energy is the one that is the most likely to form. And of course, in the case of solid to solid transformations, you can also get strains when you are creating a small clump of one solid inside another solid. For example, if the new solid that comes out requires a higher volume, its density is lower, for example, it would lead to strains being formed, and strains raise the energy and they decrease the driving force that way. So if you decrease the strains, if you think of possibilities of decreasing these strains, then you are making the nucleation process easier. Nucleation is also easier on defects or at special locations. And again, in the Veritasium video, he talks about the importance of dust. He has to ensure that the water has is basically dust free. And this experiment also works much better if you start with the distilled water with the very little gas dissolved in it, and so on and so forth. So again, dust or other such particles, they provide easy nucleation sites, and so that process where nucleation is preferred at specific locations is called heterogeneous nucleation, whereas the nucleation that we have studied so far, which doesn't care too much, I mean, doesn't say anything at all about where it nucleates, is called homogeneous nucleation. So in the case of castings, when you pour metal into a mold, the mold walls can act as nucleation sites. And there are situations where you are trying to create gas bubbles by heating something up, heating a liquid up. For example, everyday household experience is to boil water, and the first stages of boiling, you can see when you do this at home, typically the water bubbles start at the scratches on the vessel walls. So nucleation happens in these situations as well. So cloud seeding is something that I've already mentioned. And in certain classes of cast alloys are basically materials which are melted first and they are poured into a mold, and nothing else is done on them. They are used simply as they are produced, and typically these tend to be really cheap materials. And one example of a cheap material is manhole covers. They are cast iron based um, materials, and they are simply cast into that shape and nothing else is done. When I say nothing else is done, I mean what can be done after something is cast. For example, heat treatment can be given. So many automotive parts, even when they are cast, they are given some heat treatment, and so on and so forth. So in such cases, I mean, you may want to throw in something called inoculants to aid the nucleation process. And so that's again another interesting example of these inoculants are basically like dust in the case of these liquid alloys. Okay, there is also 2D nucleation, and here I'm giving you an example. So in the case of crystal growth, if you imagine crystals growing layer by layer, so you have formed one flat layer, which is basically like a crystallographic plane, for example, and the next layer, for it to start and grow, you need nucleation, and it is basically 2D nucleation. There again, the geometry comes because the formation of a little island happens under a driving force, and that depends on the area of the island. Whereas the interface that we are talking about is the circumference of this island, which is a step. And of course, the interfacial area here would be the, well, if it is a circular step that you are trying to create, it is 2 pi r, as opposed to the volume, which is pi r square, which goes as pi r square. So you have, again, exactly the same sort of geometric argument. R wins over r squared, and therefore it is difficult. So you need to create the conditions. You have to make it easier for these steps to form quite readily during crystal growth. And of course, in certain cases, you may not want crystal growth to happen in a certain way. In that case, I mean, you may actually exploit this process as well. So that's pretty much it about nucleation. And of course, growth is something that is again quite interesting. In solidification, further growth is spontaneous as long as the temperature stays below the melting temperature. But the growth rate itself would depend on the rate of heat removal, because liquid has a higher enthalpy, and all that high enthalpy will have to go out in the form of latent heat being released, and that latent heat that is being released has to be transported away. So growth rate definitely depends on the rate of heat removal. And since solid surfaces are anisotropic, the growth rate depends on crystallographic orientation. So in the case of solidification, the growth of the solid along some directions is easier than growth along certain other directions. In FCC metals, for example, the 100 directions happen to be easier. And this leads to the formation of dendrites. In some cases, it leads to the formation of columns of grains in the case of directional solidification. Directional solidification is one where you start the solidification process at one location, and heat extraction is exclusively along that direction. And I have several other tabs on my browser here, so let me see if we can see some examples of this stuff. Okay, so here is an example of a zinc oxide that has been grown on a substrate. And you see all these columns which are going directly up here. And that's because along that direction, the growth is much easier. And therefore, even though right at the bottom, many different crystal orientations would have been formed, so pretty soon, the ones that have the favorable orientation, they grow quite fast. And so the top surface is here, and it is basically polycrystalline. And if you look at the crystallographic orientation of any one of these grains, it would be the direction inside this crystal, which is parallel to the growth direction, would be roughly the same for all these grains, columns. Okay, I have another tab here. So in the case of castings, for example, this is a mold, and you have poured the liquid into it. And since mold is the coldest place right at the beginning, that is where lots of grains are formed very quickly. And they all have all kinds of orientations, and they are called the equiaxed zone. So right at the mold wall. But again, because heat extraction in this case is primarily along, primarily normal to the mold walls. So at the bottom wall, I guess heat is being removed in the downward direction. Here it is going left, and there it is going right, etc. So out of all these possible grains with all kinds of orientations, those with the favorable orientation sort of grow preferentially over the others. And they end up producing all these columnar grains, and that zone is called columnar growth. And the central region is the last one to grow, and there again one ends up producing equiaxed zone. If that's simply because this stuff has had enough time to produce other nuclei deep inside, and they all grow, and eventually they impinge on the other stuff, and then therefore they all have roughly equiaxed shape. Equiaxed as in equal distance along different directions. And I have a couple of these videos as well, so I might as well show them. This is in a simulation though. So this is a columnar growth in a 2D crystal simulation. So you see all these grains that are growing preferentially along specific directions. And of course, they produce something called dendrites. Dendrites are basically Christmas tree-like. Dendrite apparently means tree. So you see there's a central stem. And then, of course, there are side branches and so on and so forth. And towards the very end, so something which could in principle lead to equiaxed grains is shown here. I will send you the link to this particular video in the comments. And dendritic solidification is a practical example of a dendritic solidification. So you have to create the right conditions for producing them. So you can see these crystals growing in this directional fashion. Obviously, in this video, the heat is being extracted in the leftward direction. And so you see all these grains growing quite nicely. Okay, that's about it. And I will stop now, and let's take some questions now. Are there any questions?
So in the surface energy, when we are talking about the positive surface energy, so isn't like at the surface, like say we're talking water, at the surface of the ice, there's water surrounding it, right? So it's not really a surface. It can form bonds with the water. Right?
It's an interface.
Okay.
It's an interface. So, and if you take the solid, if solid is stable, it just wants to continue in the solid form. And on the other side, you have the liquid. It is not as if all the bonds are broken, but the molecules of water, forget about water. Water is a molecule with hydrogen, oxygen, etc. Take a metal, and metals are easier. That is why, most of the examples that you'll find in Callister and Ritwish, they are all from metallic examples. Because, you can think in terms of atoms and so on. So an FCC an atom in the FCC lattice requires 12 bonds. And so for the atom at the surface, it has some bonds that are satisfied, those that are in the plane and those that go into the solid. But if it looks out into the liquid, it wants bonds to be formed at specific locations. So for that, the atoms on the other side must be at specific locations. So typically, I mean, it is quite clear from the structure, from at least our imagination of what liquid structure is like. Those bonds are either absent, some bonds are absent, some bonds do exist, but they are at all kinds of places. And in the case of liquid, I mean, all these atoms are also sloshing around. They don't have a fixed location. So bonds are created and annihilated, and bonds are recreated with other atoms and so on and so forth. So because of that, the interface is associated with a finite energy, and one can measure it using specialized techniques and so on. Yeah. So that is the reason. So nucleation is everywhere. Is a ubiquitous phenomenon, and it is fundamental to pretty much all of materials. Which is why in crystal growth experiments, for example, on YouTube, if you look for how crystals are grown, one always introduces a seed crystal. And the purpose of the seed crystal is, okay, one seed crystal will allow you to actually grow a nice large single crystal. That is one nice feature about this. But the other feature is that, I mean, if you take copper sulfate, supersaturated copper sulfate, and then keep it there, it could remain in that situation for a very long time indeed. So you have to provide some way in which nucleation can happen. And by introducing a seed crystal, you're doing that. I mean, conceptually, nucleation as a phenomenon is very simple to understand. It is just pure geometry. It has nothing to do with materials. But in material science, it has enormous implications. So, which is why, I mean, yeah, it is an active area of research, and it will continue to be an active area of research for long periods of time. Yeah. Every time some new material is discovered, for example, then you have to worry about how to make it, how to make it in specific forms. If you want it in the form of directionally oriented crystals, or you just want a single crystal, and so on and so forth. I mean, it is something that you will need to worry about all the time. Anything else?
Sir?
Yeah.
So with respect to casting, wherein different regions cool faster with respect to the other, and it's so not uniform, and so you get kind of boundaries. How does one ensure that the casted material is strong and doesn't like just
okay,
fall apart?
I mean, that's an interesting question. Okay, we didn't discuss it during the lecture. Imagine a situation where you are able to create lots of nuclei and they all grow and eventually impinge, right? That situation will produce a structure. Right now, let's not worry about this columnar grains. So let's just think in terms of grains that are nucleated at different locations and they all grow. And we are comparing two situations. One situation where nucleation is difficult, very few nuclei are formed. And in the other situation, you have lots of nuclei that are able to form, and they all grow. And then, so obviously, the second situation will produce finer grains, right? I mean, that is something that you see intuitively.
Yeah.
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 Okay. So in cast aluminum alloys, for example, that is, these are cast and they are used in that form only without taking them through any heat treatment. You are just using it as is. And we haven't looked at mechanical behavior. When we do see that, when we do get there, we will realize that at low temperatures, alloys are stronger when they have finer grain structure. And that is why, I mean, in the case of aluminum alloys, these so-called inoculants, these are basically powders of oxides. extremely tiny, fine powders of oxides that are introduced into the metal, liquid metal, and they are stirred, and so that it is all uniformly distributed. And then you pour it into the mold, and these provide lots of heterogeneous nucleation sites. And since these are dispersed all over the place, so you have nuclei that are also produced all over the place, you get a nice fine-grained solid. Yeah.
So here we are going for a non-uniform graining pattern.
No, if you don't do any of that, you will get non-uniform graining shapes. Right at the mold surface, you will have lots of grains with all kinds of orientations.
Yeah.
And very quickly, it will transform into a region of columnar grains, because see, in the case of liquid metal inside a mold, the mold wall is the region through which you are taking heat away. That means heat extraction direction is fixed at a given location, right?
Yeah.
And that means the solid is going to grow preferentially in the opposite direction.
Yeah.
And if the grain, consider two grains, one which is unfavorably oriented, that is, its easy direction for growth is not along this heat extraction direction, and another one in which it is aligned with the heat extraction direction. So the second one is going to win over the other. Suppose we have two neighboring grains, and one of them is unfavorably oriented, the other one is favorably oriented. The favorably oriented one will grow very fast, and it will basically swamp the other guy and make that guy stunted. So that's it. So that guy is stuck there at near the mold wall.
So, but doesn't this non-uniform grain pattern like give rise to brittleness of the material?
Not really. I mean, metals are in general quite, especially the FCC metals, they tend to be quite ductile. They may not have the properties, but see, I mean, we are talking about situations where you are willing to live with this simply because that material that comes out of this process is very cheap.
Okay. Yeah.
Heat treatment is an additional step where you have to heat it, hold it there in that stupid furnace for a long time, and so on and so forth. So all those things add to the cost of the material. So, I mean, if possible, if you are able to get the material immediately after casting, you can still use it, etc. That is what you would use. That's what you would do. But yeah, many materials.
We don't pay attention to like the quality of it, and we just want to get it done with, kind of thing, right? Like use it immediately.
Yeah, I mean, manhole covers. Right. So that's about as low tech as it comes. And you need millions and millions of pieces, right? And you just make them, and using iron is still, as a material, iron is still the cheapest material around. And of course, this is also a very even cheaper form of iron, in the sense that it has tons of garbage in it. Cast iron, I mean, we won't go too deep into the specifics of these materials. Cast iron has at least 4% carbon. And from the foundry, I mean, whatever comes out of it is used as is. No effort to control the composition is made other than to ensure that it has all these right properties, etc. Whereas, I mean, that's why one sort of talks about engineered materials, where you really have to control the composition. And once you control the composition, the way it is processed, if it is casting, it has to be done in a particular way. And or later it is heat treated. So one talks about engineered materials, and engineered materials come in all forms. And that is why I don't quite like Callister's description of certain class of materials as advanced materials. I mean, every material that one uses now is pretty advanced. I mean, they didn't exist in nature; they needed to be created, and they need to be done in a very precise, controlled way. So.
So also another question, is there a
Yeah.
way to perform a controlled nucleation process wherein we only want certain regions to express?
Great. How is you have seen the video about silicon growth, right? I mean,
No?
microelectronics depends on single crystalline silicon with a very precise
Okay,
orientation.
yeah.
So how is it made? By introducing a seed crystal. And I think in one of the earlier classes, I also shared a video for someone who wanted to make, I mean, at home, a single crystal of copper sulfate, I think. I don't know if you have seen that. I mean, in all those cases, one introduces a seed. But we also talked about nickel-based superalloy blades, where, I mean, in the case of silicon, you produce this big boulder and you chop it up into little wafers, and then you use those wafers for further processing, for growing all these nice transistor structures and so on and so forth. Whereas in the case of nickel-based superalloys, you want a single crystal. These are blades which are in the turbine, in the hottest parts of the turbine. The blade shape is, I mean, the contours are all defined because that comes from mechanical design. So you want the final thing to have exactly the same shape, right?
Yeah.
But you also want that in the form of a single crystal. And the way that is, and of course, it has to have the single crystal means the specific directions should be pointing in the right way inside the blade. So the way that is made is actually pretty interesting. So I'll try to see if there is any video that I can send across. But basically, you do it in a two-step process. So again, it's directionally solidified. So you start from, I mean, you pour this liquid into the mold, which now has two parts. So there is this upper part, and that is kept heated so that the liquid there is still in the form of a liquid. And you start extracting, and of course, the lower part is where solidification begins. So you extract heat primarily in the downward direction, let us say. And that produces lots of crystals, and they are all growing up.
Yeah.
Okay. Now you produce one narrow channel between the bottom part and the top part.
Oh, okay. Yeah. Yeah.
Right.
That's
so if you do it carefully and well enough, then only one of these guys which are growing up, right, going vertically in the vertical direction, will be able to enter that channel.
Yeah.
And once it enters that channel, you start cooling, I mean, slowly changing the temperature of the upper part also, so that it can eventually solidify.
So what's
the blade is taken from the upper part. So then all
Oh.
this little coiling thing is all broken out. I mean, broken up, and then the top part is the blade that is, I mean, that is used in service. Yeah. Oh, by the way, I mean the blade technology is very, very specialized. Not many people actually have this technology. And in India, I mean, DMRL, Defense Metallurgical Research Lab, has the technology, and it has been licensed to companies that make LCA, for example. In the LCA, by the way, the engine is still a foreign engine, even as we speak, I think, because that engine technology is by the way, I mean, we can make engines, but we are talking about performance here. And the engines that we in fact, there is in Bangalore, there is Gas Turbine Research Establishment, GTRE.
GTRE.
Which is a defense lab. It's it's near
CV Raman
near
Nagar.
CV Raman Nagar, right? So behind HAL and stuff, that area.
Yeah. Yeah.
And so there they have facilities for making these blades and so on. They have the technology. I mean, it is a gas turbine research establishment. Their job is to create the gas turbine that will eventually make it to the LCA as an engine. And they do have prototypes. They do have to test them and so on and so forth. They have all the right things in there, except that the performance obviously doesn't match up, which is why it still continues to run with a foreign engine. I think it is acquired either from
Germany, I
GE
think.
or GE, I think, or Snecma. By the way, engine manufacturers, jet engine manufacturers, there are only a handful across the world. The big ones are GE, Rolls-Royce, and GE has a subsidiary in France called Snecma. Both the GE and Rolls-Royce, they have their R&D lab also, one wing of their R&D lab in Bangalore, and so on and so forth. So their number is very limited, and it's a very closely guarded technology. And those guys have had the head start. I mean, they have been at it for a very long time. Because of that, their engines are still far superior to any new engines that are created by countries which started late. I mean, there is nothing to be ashamed about our inability to produce these engines. So, but it will take time to eventually get there.
Okay. So also for the term paper, you, I mean, for the given topic, you expect us to write like 2 pages or about it.
About it.
So if I want to
all
change...
the topics there, pretty much every topic there is something that we are not covering in the class.
Yeah.
So, okay, the idea is to basically tell you that it's a vast field, but some features are common, and those are the common things that we are discussing in class. So when we talk about crystal structure, when we talk about phase diagrams, when we talk about nucleation and growth, when we talk about phase transformations, they are all they will all appear in these individual classes of materials in some form or the other, either individually or in combination. So I want you to focus on what it is that you know about those materials and how the stuff that you have learned is connected to the stuff that we do in this course. So just 2 pages. I mean, I don't want anything a major thesis there. Just 2 pages.
So if I want to change my topic to something like surgical implants, so that's allowed, right? So is that
write to me, take my approval, and then do it. I don't want you to choose some inappropriate topic. I'll tell you what an inappropriate topic is. I've already mentioned that. If you choose a system, you say a transistor, okay, that's doomed right from the get-go. It is not one material. Okay, transistor is a system. And of course, if you say Pentium chip, I mean, then it's a complete gone case. So choose a material.
Okay.
So,
okay. Because I want you to focus on the material aspect rather than on the system aspect. That's all.
Okay.
Just write me a mail. Write me a mail and I'll make suggestions. 3 people have already approached me. In one case, I even suggested a minor change. All that has been done.
So we're going to have 2 term papers, right? I'm not wrong.
I'll send you another set of topics soon.
And when is the Viva? Have you decided? You told you're going to conduct
that will be towards the end. That will be after the. I don't want to mix it up with any exams or anything. So after you're done with all the exams, we'll just spend 2 days and run Viva. That Viva will cover both your term papers. In fact, it'll be primarily about your term papers and 1 or 2 questions about some random topic from the course.
So along with that, we're going to also have an NSEM paper.
There is going to be an NSEM paper, yeah.
Okay. Yes.
So, sir, what is being given now? Is that the midsem? Kind of a midsem assignment?
What? Which one? The term paper.
Term paper that we received.
Term paper. Term paper. I mean, it's a part of 2 term papers which have about what? 40% weightage, 20 and 20.
Okay, sir. Sir, and if you want to change the topic, we can't choose a topic in the list that you have given, right?
To choose something else completely different. Okay, if you want to focus on oxidic materials, if you want to go find out what they are, then that will be great. So write to me, say this is what I want to do. I want to change the topic. This is what I want to do. And if it is a materials topic, I'll say yes. If it is some, I mean, system. I mean, if you say I'm going to work on engine materials, okay, engines have all kinds of components. So which one are you going to be focusing on? Or transistors, or or whatever, mobile phone. So I don't want you to choose those topics. Choose something inside your mobile phone and say, this is what I want to focus on. Gorilla Glass appears in the list, for example.
Yes,
If
sir.
you want to take a car, you can choose windshield, for example. Yeah.
Yes, sir. Means, but if you want to change the topic, we can't choose it from the list that you have given, right?
Yes, that is correct. Choose something else. I mean, use your ingenuity. Materials, I mean, there are thousands of others that you could have, I could have listed there. I got bored with it beyond a point. I said, what the hell am I doing? So choose something else.
Yes, sir. Thank you.
So just to clarify on the timeline, originally you said about 2 weeks, right?
Yeah.
So just to roughly accommodate this into our schedule, could you tell us when this would be due?
5th of January.
Okay, thank you.
We can run with that. And sometime next week, I'll send you another set of topics and we will use a similar process. There may be some overlap because I cannot be thinking of new topics all the time. So, you will get 2 more weeks on that topic as well.
And
So-
sir, would you be okay if I wrote to you about a particular clarification in my topic? It's
Do it,
one of
do it.
those materials with
Don't send
best.
me mail. Don't send me mail. Send a mail to that particular address that I've given you.
Yeah.
Okay. Yeah, you send a mail because it goes to the TAs as well. So, yeah.
So that mean also, I think that will be the entire team address, right? So that will be going
No,
to everyone
no.
else as well.
No,
Okay.
please do not do that. Do not send a mail to my personal address. Do not send a mail to the team address. Team also has an email address, email ID. That will go to everybody, I think.
Okay, sir.
So, but I have given you one address. I think it is intromsc.2020@IISc.
Yeah.
It's there in that document that I sent you,
Yeah.
or in that comment that I made. So please send a mail to that address. And I mean, I have responded to all the requests that have come. So right now there is nothing pending there, I think.
Also, sir, which week do you plan to take the Viva, and will it be there? You had said
after
about a
the
Viva.
final, after the final
Okay.
exam.
Okay, sir.
Okay, finish your final exams and then give me a 2 or 3 day window during which we will be able to just run a Viva. Viva will be for about 5 to 10 minutes. I mean, you are 120 of you, so even if we share the task of running the Viva between me and the TAs, it will still take, quite a substantial amount of time. So some 2-3 days will be needed for us to schedule these Vivas.
Okay, sir. Okay.
Anything else?
No, sir, I think that's all from our end.
Okay, great. So, well, you can log out now and I'll see you all on Monday. By the way, the next home assignment is also up. That will give you enough practice for you to, for the next 2 quizzes, which will be on phase diagrams. There are still some more questions that I want to pose. I'll send them out in another lot. But right now, I mean, a bunch of questions are already there. Most of them are from the textbook. And they should give you enough practice on the kinds of questions that you can pose in terms of phase diagrams and how you can answer them. Yeah. Okay, we'll stop now then.
Thank you, sir.